Welcome back to this lecture on uh, doing a fine tune of an LLM model hands-on. So this is the last of the week 10 videos. So for this, I'm going to go into the console. I'm going to use Vertex AI's model garden. So let's bring that up. A model garden actually comprises of a variety of different types of foundation models as well as fine-tuned models available for various types of use cases that you might think about, like text extraction, audio recognition, speech recognition, and things like that. Um, it also has the foundation models, which are natively available as downloadable libraries with weights, and you can use that within the Vertex AI Studio in order to build your own version of a fine-tuned model. And that's exactly what we're going to do. Apart from it, it also has integrations with open source library providers like Hugging Face, as well as Llama 4 and other open source weights, open weights kind of architectures as well. And then there is the class of models which Google itself promotes under Gemini, and its open source, or rather, I should say, open architecture version, which is Gemma. So for our purposes, we're going to work with Gemma 2.0. It doesn't matter, actually, you can choose Gemma 2.3 as well, or rather Gemma 3 as well. So let's see which one we want to use. Yeah, so I'm going to go into this fine-tunable models category. Let's click on Gemma 3 for now. And let's walk through the process of fine-tuning this. You can read about the documentation of how Gemma 3 was created and what are the latest set of knowledge that it has, etc. In this tab. I'm just going to go into fine-tune directly. And in that, there are a few specific items that you might want to take into account. First is the base model. The base model actually has only two types here, but if you choose something like Gemma 2, there are many more types. Uh, so one of the qualifiers in the base model, or the model name, is in this case 1B. 1B stands for 1 billion parameters. These are large language models, but even by their standards, 1 billion is actually small. So there are much larger models as well available in the broader ecosystem. IT stands for instruction tuned. This means that the model is uh, fine tuned for taking instructions and providing responses to those instructions. So basically, amenable for chatbot kind of an experience. So I'm going to let it be. I'm going to use the instruction tuned model. The output directory that I want to create the model into, the fine tuned model into, should be some kind of a GCS bucket. So let's go ahead and choose. So in this case, for instance, I've just created a directory called week 10 in my GCS bucket. If you have not created this, please go ahead and do it. And I've got few different folders here, but for my purposes, I'm just going to use this fine tuning folder. And then in that, I've created an input directory and an output directory. So the output directory is what I want to choose. So I'm going to choose that, and I've clicked on that as a select. Let's confirm this. Yes, the output directory is here. The service account that gets attached to this is the service account with which the entire fine-tuning exercise runs. So the fine-tuning exercise itself is going to be a job that's running on a compute engine account. In this case, the compute engine that's going to get used is an Ultra GPU A2 variety with an NVIDIA A100 accelerator GPU. So there are 8 accelerators because fine-tuning is a pretty expensive job compared to just inferencing. So this compute engine requires a compute engine default service account. So I'm just going to use that. That should suffice. Alternatively, if you have created a project-wide service account, you can use that as well. A region is fine. I'm just going to let it be. The default parameters in the tuning side, I'm going to let it be. The data set. So here's where we need to pay attention to what kind of data we want to tune it on. So remember that LLMs, the data is actually the way in which you get the final layer of performance from the foundation layer up to the fine-tuned models layer. And in this case, because it's an instruction based request response that we are looking to build, the data set has to have something similar in terms of format. In fact, there are two data sets required. One is the fine-tuning data set itself, which can be as little as hundreds of samples all the way to thousands of samples. And then there is an evaluation data set, which is usually smaller. It's for the model to gauge whether it's doing well on the evaluation set after every iteration, after every epoch. Now, if you don't know what the format is, you can click on the view example format and you'll get a sense of what the format is expecting. In the case of Gemma 3, or this model specifically, it's a JSON NL format, which means it's JSON completely, you know, collapsed into a single line such that every line is a new JSON record. This is unlike the way JSON is conventionally represented for human readability, which is multi-line, multi-block systems. Okay, so each line is one JSON file, JSON record, and the JSON record is of the format messages, which is one overarching keyword. And within messages, there are three types of roles. One is a system role, which basically has the content of the instruction that needs to be, carried out by the fine-tuned model. So in this case, the instruction says you should classify the text into one of the following classes, etc. So this is an example format. We'll take a look at what we have done for Iris. And then the second role is a user, which is the role that's used for giving the current sample that needs to be that needs to serve as a prompt, right? And then the assistant role, which is the third role, provides the answer for that prompt. So the system role is a instruction for the entire system, which is a fine-tuned model. The user role is the prompt itself, or encapsulates the prompt, and the assistant role responds back to that prompt with a response, and then this goes back and forth with user assistant, etc. So that's the example format. What I'm going to do is I'm going to point it to the already provided input data that I've created for this exercise. So let me go ahead and click on week 10, fine tuning, input. There we go. So I mistakenly named it as Gemini format, but it's actually a Gemma 3 format. So that's my input data set. And then the evaluation data set is also there. So buckets, MLOps, week 10, fine tuning, input, and eval. Great. So then if I click on start tuning, it's going to run like a fine tuning job for some time. Let me show you an example of a fine tuning job. Since I've already done this and it takes quite a lot of time, almost to the tune of 30 minutes, we can't really be running it and waiting for it to finish. I've already done one fine tuning job for this Gemma 3 exercise. I'll show you what the UI looks like. Before I get there, let me show you what the data looks like. So the Gemini format for Iris looks like this, right? So each line is one JSON record. The system role has the instruction classify the flower based on its measurements into one of the following species. So I've given the classes themselves in square brackets. And then the user examples here are all the specific measurements of the Iris dataset. This is basically that CSV file converted into this messages format in JSON NL. And the assistant is given the ground truth label for that particular measurement, which is setosa in this case. So likewise, I've got the entire Iris CSV file generated like this. And for the evaluation data, I just picked 10 random samples from here. It's not the right approach because evaluation needs its own samples which are not in the training. But for this purposes, for this exercise, I'm just using the 10 random samples from this as the evaluation. Let's go back to the fine-tune, the fine-tune tab. Let me show you what the fine-tuning runs look like. Pipelines. Okay, so the Gemma 3 model, which I fine-tuned with 1 billion parameters, instruction tuned model. Let me open that up. You'll see that once you click on fine tune, this kind of a UI or a URL will be available to you to track the progress. So this basically is a pipeline run. The pipeline run is of type Gemma 3 1B IT, and it's got some specific runtime parameters which you have provided, which is basically the output directory, input directory, tuning parameter, etc. So within this, you see that there are a bunch of steps that it executes by default. And then if you have chosen to optionally deploy the model, then the optional deploy step will also get activated. I've chosen not to. I hope you didn't click that because that takes its own time and there are various gotchas on deployment of a model into an endpoint. So we're not going to go through all of that, but suffice it to say that it's fairly complicated for a brand new project to get a model deployed successfully, because there are lots of quotas and system limits attached to use of GPUs in endpoints, and you'll have to go through the Google sales team after a point in time beyond a certain range of CPU or GPU utilization, and that has its own latencies attached to it. So let's not deploy the model. In fact, we're going to use the fine-tuned model directly as an import using Hugging Faces libraries like transformers and accelerate into a notebook, and that's how we're going to do this entire exercise. So when you click on Start Fine Tune, you can come here and start seeing the progress. The tuning pipeline will have like a progress circle attached to it. Likewise, the prepare tensor board, the tune model, upload model, etc. Now, what's happening here is that the foundational model, which is Gemma 3 1B IT, is taken, and the input data sets which you have provided for Iris gets attached to it, and then it learns the final layer and fine tunes and provides the final output of the model into a specific set of model, PyTorch bin files, along with a bunch of other associated parameter files, and then those get placed in the output directory. That's what the upload model talks about. So all of this is already done. So in my earlier run, it took 23 minutes roughly. It might vary based on how big your data set size is, but usually if you don't change any parameters, the Iris line pipeline should run in this time. Okay, so once it's run, automatically Google Cloud helpfully deploys this into its own model registry. If you use your own model registry, let's say MLflow's model registry, then you can configure that as part of your pipeline, or you can do a separate job to take the model from here and upload it there. In my case, I'm just going to leave it as it is. So the model registry that I've populated, I can take a look at all the models. So this model that I'm looking at right now is the fine-tuned model that got created by the job then. And there are various options available. So you can create a separate evaluation, which is hand evaluation. Here you can give separate data sets, etc. You can also deploy and test this entire model into a pipeline. And when you do that, you actually go through a variety of different choices on what kind of a machine you want to deploy it, etc. If you remember from the earlier week's lectures on deployment options for machine learning models, the same considerations apply here, which means that you can either deploy as an API, which is what this endpoint is, or you can deploy as a package, in which case the package gets imported into the code, which is what we are actually going to do. Okay, you can also configure batch inferences by giving a bunch of data sets at one time instead of giving a single data set, and then you get helpful information on when was this version created, lineage information, etc. So for our purposes, the where do we go? Yeah. So the model output is going to be present in this particular GCS bucket and the folder. This is the same folder that we have configured as output directory. But within that output directory, it's created the subfolders, which is the model name and the merged model keyword. So that's where we can find the PyTorch bin, right? So let's go confirm that's the case. So I'm going to open up a new tab, go into cloud storage, buckets. Week 10, fine tuning, output. There we go. 1750, the last digits are 3537. What did we find here? Yeah, last digits are 3537, 1750. Yeah, okay. Within that, you see merged model. So once I click on that, you'll see the PyTorch model bin. So that's your main model. The rest of it is basically useful associated modules. The PyTorch model bin is 2 GB in size, and that's for this 1 billion parameter. Imagine a 7 billion parameter model, or even higher, then the models become really, really large in size. Anyway, so that's our fine-tuned model. It's as easy as that. What can we do with this fine-tuned model? We are now ready to take this fine-tuned model and start applying this to our Iris dataset. So for this though, I've got to go back and open up our good old friend, the workbench instance, because I'm going to run a notebook into which I import this entire model. So let's go back here and start it up. But before I start it up, let me just point out a few changes that I've done to this instance. So because we're going to run GPUs, and this is the end of the course, we're going to incur a bit more cost, right? Which means that the model, the fine-tuned model, requires a GPU to run effectively, and the GPU options is something that you can convert this workbench instance into by going into the hardware tab. But you can only do that when it's in the stopped state. So don't start it yet. Go to the hardware tab. In that, there are two options, general purpose and GPUs. General purpose is the default, and that's what you've been using all this while in this course. So go instead to GPUs. By default, um, the G2 series gets highlighted, which is G2 standard 4. NVIDIA L4 and one number of GPUs also gets highlighted. Now, if you don't see any of this, if you don't get this option at all, then you are likely subjected to a quota restriction, which is what usually happens by default to all brand new users, right? So if you are subjected to quota restriction, so here's what you can do. Go into console, go into IAM and admin. The IAM part configure security, but the admin part is what we're interested in. Within this IAM and admin, you'll see a tab that's called quotas and system limits. So here, the quotas are adjustable. Firstly, you'll see what quotas are available for you, and then the quotas are adjustable. So while it loads up all the different quotas which are possible, let me helpfully start filtering some things. We are not interested in any other region for our lab except the US central one. So let's do that filtering. We are also not interested in other services beyond Vertex AI. So I'm just going to filter that as well. And now you can start filtering on the name of the quota. So for instance, if you've got uh, CPUs that you need, which are more than the default available to you, then you can attach more number of CPUs to your, rather you can claim a higher quota. So one of the most important parameters here is, for instance, custom model prediction preemptible CPUs, which means these are spot instances that you can attach to your workbench instance and get more. So for instance, I've converted this already. So the custom model prediction preemptible CPUs per region, my default value says 4. If you have not changed this before, then your default value will likely say 0 or maybe even 1, right? So once you've identified one of the quota restrictions that are preventing you from changing the workbench instance type to GPU, note down what is the quota that's getting exceeded. You'll usually get a helpful quota name, like for instance, custom model prediction preemptible CPUs per region. It'll be in camel case in a single word, or it'll be all GPUs for user ID, right? Something like that. So then you can come back here and do a name search after doing these two filters, and it will helpfully narrow down that particular quota value that you need to tweak. So in this case, I've narrowed it down to this particular value. And if you see here, the current usage is 0, which is great, which means my workbench instance is not using it. The value that's available to me is 4, which means I can go up to 4 preemptible CPUs or spot CPUs. If I need to change this, click on this vertical ellipses and click on edit quota, give the new value, and then you'll have to give a description. So I don't need this new value right now, so I'm not going to click on next. But if you do, it will also ask you for your phone number and email. Maybe I'll just show you what that is. Yeah, phone number and email, and then you can give this. And once you do this and click submit request, it goes to the backend for the GCP support team. You'll get an automated email that says we have received your request for quota increase. If your quota request is rejected for whatever reason, usually you will get a rejection email within 5 minutes, right? On the other hand, if it's going to get approved, or rather if it's not yet rejected, then you can wait up to 24 hours or 48 hours for the quota approval to go through. In practice, what I've seen is the time it takes for a quota approval is variable. There is no fixed time. Up to 48 hours is what the Google promises. In fact, I think it's 2 business days. So make sure you do it on a weekday, first thing in the morning, so that you get access to all these quotas by the time you actually want to do the work in the weekend, if you're a weekend kind of a person. Um, in practice, I've also seen that sometimes the approvals come within like an hour. So it really depends. It really varies based on your luck. Sorry to say. But yes, quotas are a thing and you'll have to work through them. Okay, let's come back. Assuming the quotas are all sorted out, let's go back to the Vertex AI Workbench instance. And the GPU instance type is what you want for these week 10 and week 11 exercises. So I'm going to create, rather I'm going to convert the hardware into this GPU instance. And since my instance is already a GPU, in fact, it's the same instance, I'm not getting an option to click on submit because it says the configuration has not been modified. But in your case, you're moving from general purpose to GPU, so therefore the submit button should be highlighted in blue. So you should be able to click on that. The good part is this is a relatively quick operation. So going from submit to actually having the hardware getting upgraded, it's about like a 2 to 5 minute affair. Please note the cost. It's really expensive compared to the the CPU instance. But the good part is whatever was the setting for automatically turning down the compute if it doesn't have activity for 30 minutes, that continues. So hopefully you're not changing that, so that even if you're accidentally allowing this to run, you're going to get cost associated with 30 minutes of inactivity maximum. Cool. So let's come back here. The hardware is set to GPUs. I'm ready now to start executing the model. So let's go start it up. Okay, it's going to take a couple of minutes for it to come up. Okay, so while this comes up, let me just briefly talk about the deployment to endpoint option and why we're not going to use that. Uh, One of the most uh, tricky things to get right is the quotas change based on which service you use. So in the deployment to endpoint model of executing the LLM, you want to actually create a VM, and that VM needs to have all the bells and whistles to execute the model, which means it needs to have GPUs attached to it, one of the NVIDIA accelerators, it needs to have enough cores, etc. What I saw when trying to do that is attaching anything more than um, a 4 CPU a 4 CPU um, machine type required me to talk to Google Sales, and frankly, the experience with Google Sales is not very thrilling at all. Multiple layers of conversations with multiple support team members, each asking the same questions again and again. So, what's the project and why do you need this, etc. That's one problem. The second part is that the reason I had to choose a model type which is more than 4 CPUs is that the RAM associated with it had to be more than 16 GB. And the reason for that is the deployment to endpoint um, option by default uses a specific set of parameters which configure 16 GB of swap space for the model. In fact, it's for the VLLM container. We'll talk about VLLM when we go to week 11 lectures. So the model inferencing, LLM inferencing engine that needs to run, the container that needs to run, needs a swap space of 16 GB by default. And changing that is quite a task because these are pre-defined scripts. Now, I could use a separate notebook to just go through this process of changing those configurations, but that's a more tedious task than just clicking on deployment to endpoint. Now, the 16 GB of swap space practically runs into the limits of available memory in the smaller CPU configuration machine types. So if you see, for instance, here, the G2 standard 4 has only 16 GB of RAM, which means the usable RAM will be roughly about 15.5 or 15.8. So when it starts running, the deployment to the endpoint starts running, the swap space immediately runs into this memory issue, and the job fails, the deployment to endpoint fails. Now, why do I need to use G2 standard 4? Why not use one of the N2 series which has a higher memory configuration? The reason is I need the latest accelerator of NVIDIA to run these Gemma 3 models. Why is that the case? Because the Gemma 3 models use something called as um, BF16 optimization for float 16 point 16 point representations. So the BF16 support is only available with the latest NVIDIA GPU compatibility versions, which is 8.0 and further. Whereas the N2 versions of the machine types only support the older NVIDIA accelerators, P4, T4, etc. So long story short, it's a lot of pain to go through. Obviously, for production use cases, you'll have to go through that process, and that's usually done once. And the sales team for a production deployment in a company is going to be a lot more helpful to you. But as an individual, I found the model import into this library notebook is much easier. Okay, that's an aside. Let's come back to our situation. Great. So the instance is up and running. Let me click on Open Jupyter Lab and bring this up. You'll find all the previous workbooks intact because all we have done is change the hardware. We have not changed anything related to the notebook itself. Okay, so let's make sure that there are no other kernels running extra because, like I said, each kernel requires its own compute and unnecessarily it eats up resources which are still in short supply in this G2 standard instance as well. I need only this Gemma plain model notebook alive. I don't need the other kernels. So let me just turn that off. Okay, good. So I've just got one kernel active now. Before I can start using my notebook against this GPU, I need to be able to use a kernel that supports the GPU, right? Now, before we get into how we do that, notice that the machine type is available as a drop down and it gives you a quick snippet of what the utilization across the different resources are, mainly CPU, GPU, and memory. So this is useful. Keep this in mind. You can use this as a way to understand what step, what cell is using what kind of resource. So what I have done is created a custom kernel. I'm calling it the Gemma GPU kernel that allows me to have the libraries that I need along with the support for GPU based processing that I need. So how do I do that? When you click on the plus icon or when you click on a brand new launcher, you'll get these bunch of options. By default, we've been choosing the Python 3 IPython kernel so far, but we can't use that directly because it doesn't have the GPU support that we need. So instead, what you can do is click on terminal, right? Terminal brings up a Jupyter Lab terminal like this, and then you can follow along with the instructions that that have been shared with the artifacts. So let me just show you what those instructions are. There we go. So we'll create a GPU kernel in the terminal by following these instructions. And in those instructions, we'll also install the appropriate libraries. So the libraries that we're talking about here are transformers, which is a Hugging Face library for working with models and being able to import them. Latest version of Torch. There's an accelerate library that also Hugging Face provides to be able to deal with multiple GPUs. We don't have multiple GPUs in this workbench instance, but it's useful. And safe tensors as well to work with compressed forms of tensors. And then we also install pandas for our users. The activate Gemma environment is basically how we're going keep adding new libraries and dependencies for this. And then finally, the display name is going to be Python 3 Gemma GPU. So this artifact is available to you. Just go ahead and install into your terminal. Once you do that, you can then change the kernel for this particular notebook. So you should be able to see this Python 3 Gemma GPU for you. Okay, great. And then I've got within the notebook itself a bunch of simple canary queries or canary code. The code basically just executes and verifies that certain basic things are available for me. So the first test here is the GPU accessible and can I read it from within the notebook? The second one is about whether the transformers library has been installed correctly, etc., etc. Yeah, so NVIDIA L4 is available. CUDA support is there. The transformers library, let's ensure that version is coming up correctly. Version 4.531, that's great. The Python executable, which environment it's running on? It's running on Gemma environment. That's great. So let's go through all of this. Okay, so we're going to build pipelines using the uh, transformers library. Now, before we do that, we need to create a local version of the model, which means we bring the model from GCS buckets into the local instance and then load that from the local instance into the transformers library. Uh, to do this, we need to copy over the entire model. Now, this model is basically the merged model subdirectory that we saw before. So, if you don't know the full URL, what you can do is go back to your storage, not specifically the Python or rather the PyTorch bin, but the merged model folder itself. You should be able to see this here. Just click on copy the paths to clipboard and you can bring it here and paste it. Notice that when you paste it, the prefix URI gs colon slash slash is not there. So just add that. With that, you're good to go. So that's your G3 model. And I'm creating a local directory called G3 plain model into which I'm uploading this model code. Yeah. So that's my local library. And once I run uh, this cell, it'll completely bring that code 2 GB of model into it. I don't need to run it right now because I've already run it before. It takes a few seconds, so keep that in mind. Then comes this cell. This cell is actually the one that's doing the work of reading the model from this merged model directory and loading it into the memory of this machine. Now, before you do this, please ensure that there is only one kernel active and also your resource utilization is as minimal as you can see. So CPU will be very low, RAM will be lowish, right, 10% and under. The reason for that is this specific model, when it gets loaded into memory, it really blows up in size, right? It takes up, it drives the overall RAM usage up to like 85%, and it takes a bit of time. So before you execute this cell, just make sure that those things are there. There's only one kernel, which is only for this notebook, and nothing else is running. Once you start running it, you'll see automatically these two resources, the utilization starts ramping up, especially the RAM. Okay, so we'll give it a couple of minutes. It takes that much time to actually read everything up from local directory. Yeah, so we see the RAM increasing significantly. Okay, so that's done. So the model has been loaded into memory. Then we've got yeah, sorry, one thing maybe I should point out, the 34% RAM is for the 1 billion parameter model, which is the 2 GB model. If you choose another model, which is let's say 2 billion parameters, then the RAM utilization will likely go up to 80-85%. So just be aware. Okay, so once this model is chosen, then I can start doing the actual exercise of instruction completion. So for this, the text that I want to do the completion on is going to be looking like exactly how I've got in my data set and also how I've got as the user part of the content in the training data, right? But the prompt I need to engineer will need to encapsulate this in exactly the same way that the instruction that has been provided to it in the training, in the fine tuning step. So that's what I've written as a function here. It helps me create a Gemma 3 compatible prompt format using the input text of the input that I actually want to give, the data that I want to give. So specifically, the system part of the instruction is bookended by these two keywords, start of turn and end of turn. And the content for this is exactly the same as what you see in the the fine tuning training data set. Then I've got the user part of the turn, which starts here, and then the actual data is what I'm passing here, right? And then that turn ends, and then the assistant's turn starts, and this is the prompt that goes into the model. Then the model gets the cue that it's the assistant, and it returns back with the completion for this assistant. because it's doing a token prediction of the next token, right? And once it's done with its prediction of the next token, which is the output of the assistant's turn, then the end of turn happens automatically and we get the response. So that's how the instruction tuning part of the format works out. Okay, so what have I done here? I've taken a Setosa example and I've given the data set pertaining to that. The Gemma 3 prompt function is called, so I'm getting the actual prompt. On top of the prompt, I'm executing few different specific things. Like one is a tokenizer, and then the tokenizer tokenizes the prompt into different tokens, and that gets provided to the model. This is the model that's loaded into memory in the previous step. I wanted to generate only 2 new tokens, like a token is a word roughly. So basically, I just wanted to come back with the topmost um, class of iris that it predicts for this specific input data set. So there are 2 other parameters. Encourage you to read about this by yourself by looking at the Hugging Face documentation. But the essence is that whenever it sees a class as a token that is generated, and that class is there in the instruction, then it can stop with newer generations, right? That's what these 2 parameters do. Okay. So once I've got the outputs are in this set of tokens. I don't need, usually the outputs comprise of the inputs as well because it's completion of a sentence. So it regurgitates the entire input prompt. I don't need the input prompt again. I just need the final class. So that's what I'm, skipping away. And then finally, that predicted class is what I'm going to use as the output of my response from the model. Okay, let's execute this one by one. So I've executed till here. I don't need to re-download. I've got the model loaded up in memory. So I've got Gemma 3 prompt defined. So I've got my Setosa class dataset available here. Okay, great. So now I'm ready to execute instruction completion for this dataset. Great. It came back with a class. It didn't error out, which is fantastic. What did it come back with though? It came back with predicted classes versicolor, whereas we were expecting a Setosa. Okay, interesting. Let's comment this out. Let's open up the versicolor sample itself and see what it comes back with. Again, it's versicolor. Okay, that's not too bad. Let's go back to our sample and see whether we can pick up an example of Virginica. Okay, so here's an example of Virginica. I'm just going to pick this row randomly and see what it has to say. Commenting this out. It says versicolor again. So for all 3 samples, it's actually predicting the same class. So let's try to increase the number of tokens and see what happens. Maybe the actual answer is there in a subsequent token, which is usually not the case, but this just gives you a glimpse of how it works. So what should have been a Virginica prediction, it's actually going through versicolor as the first class that it's predicting, and then Virginica, then Setosa, and then for some reason it's going back to Setosa, versicolor, etc., etc. So this pattern is not clear. Why is it doing that? So let's see for Setosa, what does it do? Okay, it's going through pretty much the same random-ish pattern. In other words, it's actually not doing the work that you wanted to do, which is build a predictive model based on the numerical data that you've provided to it. So here's where we're going to, dive into what you're going to do as assignment for week 10. So the essence of what an LLM is, it's a token prediction engine, right? So when it sees sepal space length, it's expecting fully a numerical value to come after that. The good part is all 3 classes in your input data set are having the same formats, which is good. But the problem is, once it sees a number, let's say 5 or 6, then it's 0.4 versus 0.5. is the token difference between versicolor and virginica as far as the LLM is concerned, because it's going through token prediction as a linearization exercise. In other words, LLMs are not great at multidimensional space boundaries between numerical data sets. It's not meant for that kind of an exercise. That's why it's overgeneralizing based on the actual token variations that it sees. And specifically, all three classes have only one decimal point. So if you look at it purely from a perspective of tokens, which is basically bits and bytes, right? The number of bits and bytes are not discriminating between the three classes. It's almost always the same. And what's more, the numbers themselves repeat across different classes. So 6.4 versus 6.5, the difference is only that 4 and 5 between versicolor and virginica, if you look at it sequence left to right, right? So in a sense, what happens now is, for this type of input data set, which is a numerical representation of the iris data set, the generalization that the LLM does, because the foundation model is very large and the input data set that's used for fine tuning is very small, is not sufficient, right? In its probabilistic prediction, mind, so to speak, Setosa or virginica or versicolor are equally likely, and in fact, it just says that versicolor is the most likely prediction all the time. In fact, if you train this model, you might find that it's always producing Setosa for all samples. So you may not get versicolor as the only prediction. So in a sense, this form of input data is not amenable for an instruction tuned foundation model to be fine tuned further on, right? So the assignment for you is, how do you convert this numerical data set into a language or linguistic driven data set such that the same semantics is maintained? I'll give you a clue. So when you see the difference between a versicolor, setosa and a virginica, you really have to take a look at the dimensional differences between these three iris flowers on all the four categories, all the four dimensions. And for this, you might find the governance notebook that you did earlier useful. Specifically, the notebook will have distributions of the values, right? So if you look at sepal width, where is the distribution? No. Oh yeah, of course. So the data distribution is here. So if you look at, for instance, sepal width, the distribution ranges from 2 all the way till 4.2, and it has some kind of a mode in the center, right? Uh, using these distribution graphs, you can bin them into how many ever bins you want. Like an example would be 3 or 4 bins, and attach qualitative descriptors for them: low, medium, average, high, etc. Right? 3 bins is good enough. 4 is okay. 5 is maybe too much of an effort. I'll leave it to you. It's up to you. But you will come up with a qualitative description of each data point, of each record in that particular file, such that the numerical data set becomes a linguistic data set, becomes an adjective driven descriptive data set about that flower. So what this also means is that you might have multiple samples which look exactly the same because you've binned them naturally, right? So make sure you do this for both the sepal dimensions and the petal dimensions. Redo the entire training exercise of the fine-tuned model, and this time try it out with a different foundation model. Try it out with Gemma 2. That will be your assignment. So in a sense, convert the iris dataset into textual format. Use Gemma 2 for fine-tuning, which means you need to create the right fine-tuned format for Gemma 2. So you'll go through this exercise of changing the format as well. So that'll be useful for you to keep in mind. And then you'll take that model and plug it into a notebook like this. Appropriately change the prompt as well, of course, and see what it produces as output. Okay. Thank you. I'll see you in week 11.